Today we're going to talk about what it means to be a series, and then we're going to focus on arithmetic sequences. First, with a series, this is basically some or part of a sequence. So if you recall when we talked about sequences the other day, we talked about how a sequence was a list of numbers. A series is when you sum or add all of those numbers. As far as our notation goes, we use this sigma sign. And you might have seen this sign before if you've used any spreadsheets in Excel. It's used to sum up a list of numbers. In this problem, in example 12, the n equals 1 on the bottom, this is the starting value. The 5 on the top is the ending value. So basically what that means is that we want you to find a1, a2, a3, a4, a5, and instead of listing them as a sequence, we want you to actually add all of the values together. So your answer will be a single value. For this first problem, if we plug in 1 for n, we can get a1 to equal 5. If we plug in 2, we will get a2 to equal 7. If we continue in this fashion, we get 9, 11, 13, and when we add all of these values up, we get 45. In example 13, notice that we are not starting at the first term. We are starting at the third term. Therefore, we want to do a 3 and so on to a 7. So if we add up each of these terms, 9, 16, 25, 36, and 49, we end up getting 135. On this slide, we want to go ahead and find the series as we see them. Go ahead and do the first two, and we're going to pause the video. What you'll see here are each of the terms and then their sum. When I'm grading you on problems like this, I will want to see that you have written out all of the different terms and then show me what the sum is equal to. Notice on example 15 that the starting value is 2 and we are not starting at the first term. On example 16, this one is slightly different, and that's because this is an infinite sum. And in this case, if you imagine what's going on, and we found a 3 plus a 4 plus a 5 and so on, each time, based on the -7 coefficient, the number would decrease by -7. It would never converge to a specific number. It would just keep on getting more and more and more and more negative. So if we tried to add all of the terms to infinity, to the infinity term, well, we can't exactly get a value there. This is what we call a divergent series. And when we are dealing with divergent series, you can't find the sum. It doesn't exist. We say that it does not exist because it does not approach a specific value. An acronym that we use for does not exist is DNE. So you can either write does not exist or DNE. You do not want to write infinity. On these problems here, what we want to do is describe the series using sigma notation. Sigma notation needs several pieces. First of all, we need to have the sigma symbol. Then we need to say n equals and a starting number. We need to have a stopping number. And then we need to have the explicit formula. Remember, the explicit formula is what a sub n is equal to. We do not actually write the a sub n, though. So if we look at example 17, we have 1, 2, 3, 4, 5 terms. So I'm going to start by saying summation from n equals 1 to 5. Now the variable that you use here could be anything. You could use n, you could use k, j. It really does not matter as long as you are consistent through the problem. If we look at example 18, here I see 4 terms. However, I have this dot, dot, dot. And what this dot, dot, dot means is that my summation goes on until infinity. So I would say summation n equals 1 to infinity. And then for this last one, I have 1, 2, 3, 4, 5 terms again, so summation n equals 1 to 5. So this is always our starting point that we need to have. Now, we need to go ahead and actually figure out, well, what is the formula? If we look at our first problem, each time I am adding 4. And we talked about how a simple way to come up with this formula is to start with the expression 4n. However, if I used this formula and had n equal to 1, that would make my first term 4, which is too big. It's too big by 2 units. So then what I'm going to do is write -2 to fix my formula. Finally, I want to test it. When I plug in 1, I get 4 minus 2, which is 2. When I plug in n equals 2, 8 minus 2, which is 6. And I can do this a couple times and verify that, yep, my formula is correct. When we look at example 18, using a similar idea, we will recognize that all of these are 1 over perfect cubes. So we could write our formula as 1 over n cubed. You could also write n to the negative third power, however we prefer our exponents to be positive. In example 19, I want you to notice two things here. First of all, I want you to notice the alternating negative signs. Secondly, I want you to notice the multiples of 3. When we have adding of the same number, like in number 17, we see that number as a coefficient on n. So since I was adding 4, 4 becomes my coefficient on n. When we see multiplying by the same number, then that's when we start seeing that as a base raised to an exponent. So these are all powers of 3, which we could write as 3 to the n. Now the fact that I have a negative sign in there, there's a couple different ways we can handle this. One way is you can put the negative in with the 3 and see if that gives you the proper negative signs. So when I plug in n equal to 1, I get negative 3. When I plug in n equal to 2, I get positive 9. And then this right here, I can see does the trick. I must have the negative sign in parentheses. If I don't have it in parentheses, then what that is saying, I'll just make a note off to the side. If I had written my formula like that, that would be negative 3, negative 9, negative 27. It's basically saying negative of all the powers of 3. If my first term had been positive, then in this case, I would have to put my negative 1 off by itself and then multiply that by 3 to the n. And what this does is this offsets where the negative appears to make it not start with our first term. Alright, today we're going to focus on what are called arithmetic sequences. Now I know we're used to seeing this word pronounced as arithmetic, but for whatever reason, when we are talking with sequences, the word is pronounced arithmetic. It almost sounds like there is a D there instead of an ET. Alright, so all arithmetic sequences are sequences where each term is separated by a common difference, and the way that that looks is like the same number being added or subtracted each time to the previous term. Now we talked yesterday about simple ways we can come up with formulas involving always adding 3 or always subtracting 2. Those simple methods still work. However, what we're going to do now is teach you an explicit formula that will work in every case, even ones where the numbers don't work out as nicely, and it's definitely useful to know this formula. Right here, this is our first formula that we really want to memorize, and it's for the nth term of any arithmetic sequence. And the way that this term is broken down, a sub n is basically for any term, a sub 1 is for the first term, n is for the term that we are on, and d is the common difference. The way that we find the common difference is by taking one term and subtracting the previous term. So in this case, for example 1, I would do negative 3 minus negative 7, which is 4. When our common difference is positive, it means that we are always adding the same number. When it is negative, it looks like we are subtracting the same number. So if I were to look at this pattern right here, if I wanted to come up with an explicit formula, I could say a sub n equals my first term, negative 7, plus n minus 1 times my common difference of 4. If I were to simplify this expression, then I would get negative 7 plus 4n minus 4, which gives me that my general formula is 4n minus 11. If you think back to how we learned these the other day, we said start with the common difference and then fix it. In this case, I would have to fix it by minusing 11. Notice that we get the same formula either way we approach the problem. On this slide, I've just listed some common tips. First of all, we always want to find the d by subtracting 2 consecutive terms. To write any equation, you need your first term and your common difference. When possible, we need to find these first. if we are given two terms, for example, the 5th and the 12th, then what we can do is we can set up a system. And that's why it is so useful to know our formula of a sub n equals the first term plus n minus 1 times our common difference. And then lastly, n is always a natural number, 1, 2, 3, etc., because n refers to which term we are. And when we are counting terms, we can't have negatives and we can't have fractional terms. Okay, so what I'm going to do now is run through a series of examples to help you see why this explicit formula is useful. In example 2, we want to find the 100th term. If we're trying to find the 100th term, then n is 100. We know that our first term is 9, therefore a sub 1 is 9. And then to get my common difference, I can take two consecutive terms and subtract them. So I can see that my common difference is negative 1/3. Remember that if our numbers are getting smaller, then our difference has to be negative. So I can now say that my nth term is found by doing my first term plus n minus 1 times my common difference. Now, since my goal is to find my 100th term, I don't need to simplify this expression. All I need to do is plug in 100 and do 100 minus 1 and get 99, and then go ahead and carry through the problem, giving me negative 24. Looking at example 3, here I know the 41st term, and I want to find my 7th term. I said a minute ago to solve for any term, we need to know our first term and our d. And in this problem, I don't know my first term. I only know my 41st term. So what I'm going to do is I'm going to solve for a1. And I'm going to say that I know my 41st term is equal to my first term plus 40 differences. Remember, the 40 comes from being n minus 1. So now if I plug in what I know, 53 equals a1 plus 40 times negative 4/3, I can work backwards and find out that my first term is 106 1/3. As you can see, when we start dealing with fractions, using these formulas becomes a necessity. Now that I know my first term and my difference, I can now go ahead and answer the question that I want to solve. What is my 7th term? My 7th term is my first term plus 6 differences. So my first term is 106 1/3 plus 6 times my common difference of negative 4/3. And when I go ahead and work that out, I get 98 1/3. As you can see, a lot of these problems involve calculations that most likely you would use a calculator for. Make sure you have a calculator every day, and I would highly encourage you to make sure you have one with a fraction key. Okay, in example 4, we are asking you to find n. So we're essentially saying, which term am I referring to if that term is 32, my first term is negative 10, and my common difference is 7. Now, you can think through this in one way and saying, okay, if I start with negative 7, how many times do I have to add 7 before I get to 32? And that can definitely get you the answer. Now, if it happened to be that you needed to add 7 like 85 times, that would be really annoying. So let's talk about how we could solve this for any nth term. I know that my nth term is my first term plus n minus 1 times common difference. So I know that 32 equals my first term plus n minus 1 times 7. And now this is just a simple algebra problem that we can go ahead and solve. We get 49 equals 7n, therefore n equals my 7th term. Now remember, n must be a natural number. So if you go through this process and you end up getting something like 2.4, then you know you did something wrong. Now in example 5, we are given our third term and our 31st term, and we want to find our common difference and our first term. What I would suggest for this kind of problem is to set up a system. We know that my third term is always my first plus 2 differences. So I can say that 16 equals my first term plus 2d. And we know that my 31st term is my first plus 30 differences. Therefore, 144 equals my first term plus 30d. And these two equations set them up very nicely for elimination for solving my system. So I'm going to go ahead and recopy this left equation down here, and then subtract the equations, and we end up getting 128 equals 28D. When I divide, I get that D equals 32/7. It is okay for my common difference to be a fraction. It is not okay for my n to be a fraction. Now that I know what my common difference is, I can go back and plug it back in. So I'm going to plug it into my equation over here on the left. Say 16 equals A1 plus 2 times this common difference. And after we multiply and then subtract, we find out that our first term is 48/7. Yes, these numbers are ugly and nasty, which is all the more reason why you need to know your formulas. Alright, we're almost done. Just one more concept to talk about. The last concept is what's called an arithmetic mean. And an arithmetic mean, these are going to be the terms in between any two non-consecutive terms of an arithmetic sequence. It's kind of like playing the game of fill in the blank. So if I look at what I see down here, 38 and 49 are the arithmetic means between 27 and 60. So if this is 27 and this is 60, 38 and 49 are basically the numbers that are in between them within our arithmetic sequence. So if we take a look at this, we can see that each time we are adding the same amount, and we know that we're adding the same amount because it is arithmetic. We can see here that I'm adding 11, and so on. So if I was asking you to find those missing numbers, then we could go ahead and solve an equation. Now, one thing that I want you to notice is that if I am trying to go from 27 to 60, I have to add once, twice, 3 times. So if there are 2 missing terms, I need to add my common difference 3 times. So I could write an equation saying 27 plus 3D equals 60. And then knowing that, I could go ahead and work backwards to solve and find out that my common difference was in fact 11 and use that to fill in my blanks. So we could kind of make a general rule here and say that if you have n missing terms, then you need to add the common difference n plus 1 times. Alright, we're going to finish up our lesson today by solving for the missing terms. So our directions say to write a sequence. What we want you to do is basically fill in the missing blanks. So there are 2 arithmetic means between -7 and 8. That means we have -7, blank, blank, and then 8. And we just talked about how we had to add our D 3 times for 2 missing blanks. So I can say -7 plus 3D equals 8, 3D equals 15, common difference is 5. Now we can go ahead and add 5. So -7 plus 5 is -2, -2 plus 5 is 3, and then if I continue that pattern, 3 plus 5 is 8. And that verifies that we have found the correct values. Go ahead and try the last example on your own. Please pause the video. In our last problem, we have 3 arithmetic means, therefore we have 3 spaces to fill, and we need to add 4 common differences. So we use the equation 3 equals 4D plus 9. Solving, we find that our common difference is 3 halves. To verify that this is the correct common difference, we can consecutively add 3 halves, starting at the 3, and then we end up finishing off with a 9. So our final answer would be the sequence 3, 4.5, 6, 7.5, and 9. Alright, that's it guys. Homework is worksheet 1B. Have a great day.